Okay, so now we move on to weak acids, right? So weak acids we know are different because they have a conjugate base that we have to worry about because the concentration of the conjugate base affects the overall pH. We saw that in the Henderson-Hasselbalch equation, right? So when we use a strong acid like HCl, we don't have to worry about the conjugate base because the conjugate base is so weak that it doesn't ever, the equilibrium doesn't lie in any, it lies only in the direction of creating more conjugate base and creating more H plus, right? So we don't have to worry about that when we use strong acids. With weak acids, we do because the base will affect the pH. Okay, so I gotta find my notes here. Really should have planned that out better. All right, so what happens when we, so now we're doing the same thing, only not the same. Titration of weak acids. And we're still using strong base. You always use a strong base when you titrate because we want to be able to control the equilibrium, and strong bases allow us to say, yep, that equilibrium, we know what side of this reaction is going to be favored. So I'm going to use acetic acid because we've talked about acetic acid a lot. Obviously, you can use any acid, any weak acid, and the math will be more or less the same, except for your pKa number will change, right? So, but as an example, to kind of work through these ideas, we're going to use acetic acid, which we know has a pKa of 4.74. Okay. So initially, let's say that we are given an initial set of conditions, and we say, okay, we've got an 0.7 molar solution of acetic acid, and we have 100 milliliters of it. So you've measured out 100 milliliters of acetic acid, 0.7 molar solution. We can figure out the pH of this, right? We find the pH from the Ka expression. Oops. Right. So this is one where, right? So initially, when you have a solution of only acid, we use the Ka expression, right? So we know that so the Ka equals the concentration of H plus over times the concentration of the conjugate base all over the concentration of the acid, right? And all the stuff we talked about a couple weeks ago where H plus and the conjugate base, these concentrations are the same. Concentration of acid is our initial concentration, and the Ka we know because we know the pKa. So we can set this equation up. 10 to the negative 4.74, right? Because pKa to Ka is the negative log, so we reverse that and say, if we're given the pKa, we can know the Ka is 10 to the negative pKa. So 10 to the negative 4.74 equals X for the concentration of H plus times X, which is the concentration of the conjugate base. These two numbers are the same, all over 0.7, okay, which is the initial concentration of the acid. And we can solve this, right? And we could solve this easily. X ends up equaling whatever the actual number is. Well, I don't have the actual number, but X ends up equaling 10 to the negative 2.44. I cheated a little bit here because what we want is the pH. So we want the negative log of X, right, equals the pH equals 2.44. So I cheated it. I got the pH, but I never wrote down what this actual X number is. So it's 10 to the negative 2.44, whatever that is. I think it's like 0.03 or 3.6 or something times 10 to the negative third, something like that. And that'll give you the pH here. So our initial pH is 2.4, which makes sense. We have a solution of acid, we have an acidic pH, everything is good. Okay? So again, if we drew a titration curve, we would start at our initial point, right? This is our initial point, is pH of 2.44. Now, what happens when we add some strong base? So I'm going to add 5 milliliters of 1.5 molar sodium hydroxide, right? Is added. And immediately what we're doing is we're adding base to a solution of acid. Now we've got base and acid, right? So a solution of only weak acid, we use Ka. Once we have weak acid plus strong base, now we have to use an ice table and the Henderson-Hasselbalch equation. So this is the one where you have to do all your this is where you make your money as a chemist, right? Being able to convert this solution into a pH value is going to be important. Oh, to find pH. Just deleting words. Right. Okay, so let's go through that because I think this is a situation that probably needs some explanation. Okay, so first of all, what's happening? We have a weak acid. I guess it's acetic acid, so I can put acetic acid. We have acetic acid plus sodium hydroxide. And the products of this are going to be the conjugate base of acetic acid plus water. Now, the good news is, of course, water we don't have to worry about in our equilibrium constant calculations because water is a pure liquid. Right? The conjugate base here, we have to worry about if this reaction is producing significant amounts of conjugate base. Sodium hydroxide is a strong base. It has a very large Kb, right? That's what a strong base means, which means this equilibrium is a Kb type of reaction, right? The equilibrium constant for this reaction is Kb, right? Conjugate base as a product, sodium hydroxide and the conjugate acid as the reactants. This is a equilibrium expression that is expressed as Kb. I don't feel like I did that well, right? If we were drawing up an expression for Kb, right? Kb is always OH minus times conjugate acid all over base. That's what Kb is defined as, right? That is exactly this reaction, right? Our reactants are OH minus and our conjugate acid, and then our product is the base, right? So if we have a large Kb, that means that the products are favored, right? So if we go back to when we were talking about equilibrium constants, implies products are strongly favored. Right? If we go back to our equilibrium constant interpretation, having a large K value for an equilibrium expression means that the products are strongly favored. So that means that when we add this sodium hydroxide in, we are going to produce conjugate base. Equilibrium constants tell us that this is true. Okay. So what we have to do now is set up an ice table. Right? Actually, let me work through this because if I can get it to work, there we go. So we have an initial concentration of sodium hydroxide, right? And that is the 5 milliliters times, 1.5 molar, right, in there. And then we have, that is going to change, this initial concentration changes as NaOH interacts with acetic acid, right? They're going to react to produce the conjugate base. And then we're going to reach an equilibrium. Changes as sodium hydroxide and reach equilibrium. And of course, all of these, I told you already that we're doing ice tables, but you'll notice that these are, of course, the 3 components that show up in there. I'm going to bump the ice table into the next video because this one's already getting a little bit long, but we're going to set up this whole thing and set up the ice table and allow you to kind of see how this works, okay? Or how we're going to set this up and how this is eventually going to lead us to the pH in the middle of a titration.